Good evening, everyone. My name is Mallada Bhavana Chandar from Lending Institute of Engineering and Technology. During my internship at Emertxe Information Technology, I developed an EV ADAS dashboard using the STM32 F1033C8T6 Bluepill Pixim Lab and Python. The objective of this project is to simulate an electric vehicle with advanced driver assistance system features. The system monitors vehicle parameters such as speed, battery charge, motor temperature, torque, and obstacle distance. It also detects unsafe situations like nearby obstacles, blind spots, and falls. Then displays all this information on a live Python dashboard. This project helped me understanding embedded system, STM32 peripherals, UART communication, sensor interfacing, and real-time data visualization. Modern electric vehicles continuously generate large amount of sensor data. Drivers and engineers need to monitor speed, battery level, temperature, and safety features simultaneously. Monitoring all these values manually is difficult. My project solves this problem by creating a single dashboard that combines EV monitoring with ADAS safety features, making it easier to observe the vehicle's condition in real time. The complete system has four stages. First are the sensors which provide input such as accelerating position, brake position, motor temperature, and obstacle distance. These inputs are sent to the STM32 Bluetooth. The EV control module calculates speed, torque, battery, SOC, and remaining range, while the ADAS module checks the collision warning, blind spots, and parking assistance. After processing, the STM32 sends telemetry through UART at 1,15,200 baud. Finally, the Python dashboard receives the UART data and displays speed, battery level, obstacle distance, alarms, and fault in real time. Real electric vehicle uses wheel speed sensors, radars, cameras, and CAN communication. In my project, I replaced these expensive components with potentiometers, ultrasonic sensors, UART communication, and a Python dashboard. Although simplified the working principle, the remaining the same and helps demonstrate how an actual EV monitoring system operates. The project was deployed in 9 phases. I first configured the deployment environment, then set up general pin input and output, ADC timers, and UART. Next, I implemented the EV dynamics model followed by ultrasonic sensor integration, ADAS algorithms, fault handling, UART telemetry, UART shell commands, and finally the Python dashboard. I used STM32 CubeIDE for firmware development and Piximlab for hardware simulation. The peripherals configured include TIM1 for the EV update every 10 milliseconds, TIM3 for sensor updates every 100 milliseconds, TIM2 for ultrasonic timing in microseconds, TIM4 for budget PWM generation. ADs for reading acceleration, brake, and temperature. UART1 for communication with Python. General pin input output pins for LEDs indicating collision, blind spot, and fault conditions. The accelerator, brake, and motor temperature are simulated using potentiometers connected to ADC channels. The ADC converts analog voltages into digital values. The EV controller modules uses these values to calculate torque, vehicle speed, battery state of charge, remaining range, and regenerative braking. Different drive modules such as ECO, normal, and sport change the vehicle performance. Three HCSR04 ultrasonic sensors are placed at the front, left, and right of the vehicle. The front sensor detects obstacles for forward and collision warning. The left and right sensor detects vehicles for blind spots. When the speed is below 10 km per hour, all three sensors assist in parking. The system also calculates time to collision using distance and vehicle speed. Depending on the calculated values, the alarm level changes from advisory to warning and finally critical. The fault module continuously checks whether the motor temperature exceeds 90 degrees Celsius. Battery SOC falls below 2 degrees 2 percentage or a critical collision is detected. If any of these faults occurs, the system sets false flags, stops the motor torque, changes the vehicle state and to fault mode, and turns on the fault LED. Every 100 milliseconds, STM32 sends to the telemetry frames. The first frame contains EV information such as speed, battery, SOC, torque, motor temperature, range, accelerator, and brake values. The second frame contains ADAS information including front, left, right, obstacle distance, time to collision, collision level, blind spot status, alarm level, and fault status. Python reads these UART frames and updates the dashboard instantly. The UART shell allows testing without moving sensors. Commands such as speed, SOC, temperature mode, fault, reset, and status help inject test values directly into the controller. This makes debugging much easier. The dashboard have five sections. A circular speedometer displays vehicle speed. A battery bar shows state of charge and remaining range. A speed graph displays previous speed values. An EV information panel shows torque, acceleration, brake, temperature, alarm, and faults. A bird's eye ADAS view displays nearby obstacles and blind spot warning. The project successfully achieved real-time speed monitoring, battery monitoring, obstacle detection, blind spot detection, fault handling, UART communication, and Python dashboard visualization. The entire system worked correctly inside Pixim Lab. This file contains all common libraries, common.h, code explanation. This file contains all common libraries, macros, utility functions, and global definitions shared by every module. Instead of writing these definitions repeatedly, every source file includes common.h, evcontroller.h. This file defines the EV model. It stores speed, torque, battery, SOC, motor temperature, regenerative braking, drive mode, and remaining range. The EV control function continuously updates these values based on accelerator and brake inputs. Ultrasonic.h. This file defines the HCSRO for ultrasonic driver. It specifies sensors IDs, trigger pulse with echo timeout and distance limits. It also declares function that measure obstacle distance. Ultrasonic.c. This file generates a 10 microsecond trigger pulse to the sensor, waits for the echo signal, measures the echo duration using timer 2, converts the measured time into distance using the speed of sound and stores the calculated distance for the ADAS module. ADAS.h. This file defines the ADAS engine. It stores collision threshold, blind spot limits, time to collision values, and alarm levels. Using sensor data, it determines whether the vehicle is in safe or danger condition. Fault.h. This file handles fault management. It checks motor overheating, battery level, and collision status. Whenever a critical fault occurs, it sets fault flags and safety stops to vehicle. UART shell.h. This file creates a command line interface over UART. It also contains a ring buffer for receiving serial commands and processing them without losing incoming data. Main.h. This file contains GPIO pin definitions generated by STM32 CubeIDE and serves as a hardware configuration file for the project. Pixim Lab hardware connections. The STM32 Blue Pill is the main controller. The accelerated potentiometer is connected to PA0 The brake potentiometer is connected to the PA1. The motor temperature potentiometer is connected to PA2. The HCS2 SR04 ultrasonic sensors use separate trigger and echo GPIO pins connected to the STM32. Trigger pin sends 10 microseconds pulse, while echo pins receive the reflected signal to calculate distance. USART1 uses PA9 and PA10 to communicate with Python dashboard at 1,15,200 baud. The buzzer is connected to PB9, which outputs a PWM signal generated by TIM4. Status LED connected to the GPIO pins indicates collisions, warnings, blind spot detection, and fault conditions. When the project starts, STM32 initializes all peripherals including GPIO, ADC, timers, UART, and PWM. Every 100 milliseconds, the ADC reads accelerator, brake, and temperature values. At the same time, the ultrasonic sensor measures distance around the vehicle. The EV control module processes the sensor values to calculate speed, torque, battery state of charge, range, and regenerative braking. The ADAS module analyzes the obstacle distance to detect collision, blind spots, parking condition, and time to collision. The fault module continuously monitors motor temperature, battery SOC, and collision severity. If any critical condition is detected, it activates fault mode, disables motor torque, and raises alarms. Finally, all proceeding information is transmitted through UART to the Python dashboard, where it is displayed in real time using gauges, graphs, status panels, and bird eye ADAS view. This complete workflow closely simulates how a real electric vehicle control system and ADAS module operate together in modern vehicle. The accelerator, brake, and motor temperature are simulated using potentiometer connected to ADC channels. I used STM32 CubeID for firmware development and FlexSimLab for hardware simulation. Here is the overview where the we see speedometer, EV ADAS dashboard, alarm done. And here we can see the mode present. The mode is in normal condition, and we can see the ADAS bird eye view uh, where the distance between the two vehicles is normal. And here the acceleration percentage is 53 percentage and brake percentage is 56 percentage and temperature is 54 degrees Celsius. Every condition is normal, so there is no alarm occurs. Now the we will decrease the distance of the front distance, and here we got an alarm of critical. The distance between the two vehicles decreases. Now we reduce the side left side distance. Real electric vehicles uses wheel speed sensors, radar cameras, and CAN communication. Now we increase the brake panel. Let's see. Here brake percent is 99% and the acceleration is reduced to 0% and torque is minus 55 Nm. Now, thank you for giving me this wonderful opportunity.